Hello, my name is Minoy Cristobal. I am from Lima, Peru. I am a master's student in Dr. Parsons' lab and former visiting scholar in Dr. Stein's Monogastric Nutrition Lab. In this podcast, I'll be presenting one of the research we have conducted at the University of Illinois in order to determine the concentration of digestible and metabolizable energy and digestibility of phosphorus in a new source of high protein distillers dried grains with solubles fed to growing pigs. Distillers dried grains with solubles, or DDGS, is a co-product from dried grain ethanol production. The inclusion of DDGS has increased in the last 20 years due to its increased availability in the market. The nutritional values of DDGS have been analyzed and reported. Some characteristics of this ingredient are great concentrations of energy, protein, and minerals. However, the nutrient content may differ among sources due to the origin and technology used on its production. Recently, a new source of DDGS, known as ProCap DDGS, was developed by isolating high protein and low fiber fractions from the solubles and drying these fractions separately. In consequence, the ProCap DDGS has greater concentrations of crude protein and fat but contain less fiber compared to conventional, the oiled DDGS. These characteristics might affect the digestibility of nutrients and concentration of energy, and there are no data about this ingredient. Therefore, the objective of this research was to test the hypothesis that apparent total tract digestibility of gross energy, concentrations of digestible energy and metabolizable energy, and total tract digestibility of phosphorus in ProCap DDGS are greater than in conventional the oiled DDGS when fed to growing pigs. Two experiments were conducted. The first experiment was conducted in order to determine the digestibility of gross energy and concentrations of digestible and metabolizable energy. 24 barrels, with initial body weight of 32 kilos, were allotted to 3 diets and 8 replicate pigs per diet, with individual pig body weight being the blocking factor using a randomized complete block design. Pigs were housed individually in metabolism crates that were equipped with a self-feeder, a nipple waterer, and a slated floor. A screen and urine pan were placed under the slated floor for the collection of urine and fecal samples. A total of 3 diets were used: a basal diet containing corn as the sole source of energy, and 2 diets containing corn and each source of DDGS. Vitamins and minerals were included in all diets to meet or exceed the current requirement estimates by NRC 2012. Pigs were limit fed at 3.2 times the metabolizable energy requirement for maintenance. Water was available at all times. The initial 7 days were considered the adaptation period to the diet. Fecal samples were collected for 4 days according to standard procedures using the marker-to-marker approach. Urine samples were collected for 4 days using a time-based method. Urine was collected in urine buckets over a preservative of 50 milliliters of 3 normal hydrochloric acid. Fecal samples and 20% of the collected urine were stored at minus 20 centigrades immediately after collection. The second experiment was conducted in order to determine digestibility of phosphorus and effects of microbial phytase. 32 barrels with initial body weight of 20 kilos were allotted to 4 diets and 8 replicate pigs per diet using a randomized complete block design. Individual pig body weight was used as the blocking factor. The 4 diets were arranged in 2 per 2 factorial with 2 sources of DDGS, ProCap DDGS and conventional DDGS, and 2 levels of microbial phytase. 0 and 500 units per kilogram of diet. Vitamins and minerals other than phosphorus and calcium were included in all diets to meet or exceed the estimated nutrient requirements for growing pigs. Housing, feeding, and sample collection were similar as for experiment 1, with the exception that no urine samples were collected and the adaptation period was 5 days, and fecal samples were collected for 4 days. Moving on to results for experiment 1, this figure shows the values obtained for apparent total tract digestibility of gross energy, where the ProCap DDGS had a greater digestibility than the oiled DDGS, but there was no difference with corn. Now we observe the concentrations of digestible and metabolizable energy obtained for the three ingredients. There was a greater concentration of digestible and metabolizable energy in ProCap DDGS compared to de-oiled DDGS and corn, even though corn had a similar apparent total tract digestibility of gross energy as we saw in the previous figure. It has been demonstrated that concentrations of digestible energy and dietary fiber in feed ingredients are negatively correlated, whereas digestible energy and crude protein are positively correlated. Therefore, it is likely that the lower concentration of dietary fiber in ProCap DDGS and the greater concentration of crude protein and acid hydrolyzed ether extract resulted in the greater digestible energy and metabolizable energy in the ProCap DDGS compared to the oiled DDGS. The observation that ProCap has greater concentration of metabolizable energy compared to corn and the oil DDGS indicates that ProCap DDGS is a well-digested energy source in diets fed to pigs. From the results of experiment 2, the figure shows the standardized total tract digestibility of phosphorus and the effect of microbial phytase on the oil and ProCap DDGS. When there was non-phytase added, the standardized total tract digestibility of phosphorus was greater in the oil compared to the ProCap. But when the phytase was added, there was no difference between the oil and ProCap. The phytase increased the standardized total tract digestibility of phosphorus in the ProCap DDGS, but it did not have an effect over the oil DDGS. For the apparent total tract digestibility of calcium in diets and the effect of microbial phytase, a similar result as the previous figure was found. When no phytase was added, the de-oiled DDGS had a greater digestibility than the ProCap, but when the phytase was added, there was no difference between de-oiled and ProCap DDGS. Again, the phytase increased the apparent total tract digestibility of calcium in the ProCap, but there was no effect over the de-oiled DDGS. The observation that the use of microbial phytase increased the standardized total tract digestibility of phosphorus and the apparent total tract digestibility of calcium in the diet containing ProCap DDGS indicates that there were enough substrate or phytate for microbial phytase in ProCap DDGS. The phytate bound calcium from calcium carbonate by forming a calcium phytate complex in the intestinal tract. Therefore, when microbial phytase was added, this calcium was released and the apparent total tract digestibility increased. However, no effects of microbial phytase were observed in the standardized total tract digestibility of phosphorus and the apparent total tract digestibility of calcium in the diet containing the oil DDGS, which is likely because a very low concentration of phytate in the oil DDGS. This low phytate content might be due to the use of phytase during the fermentation in the production process which is common in conventional DDGS. Based on the results of this study, we conclude that there are greater concentrations of gross energy, digestible and metabolizable energy, also less concentration of phosphorus and standardized total digestibility of phosphorus in the ProCap DDGS compared to the oil DDGS. Also, when phytase is used, there is an increment in the standardized total tract digestibility of phosphorus and apparent total tract digestibility of calcium in the ProCap DDGS, but not phytase effects in the oil DDGS. Finally, I would like to acknowledge the Marquis Energy Company for sponsoring this study and the Stein Monogastric Nutrition Lab for all the support. Thank you.